So this video is set up to give you guys some examples of how this electromagnetic function works, also some ways that we can take advantage of the electromagnetic field and the field of magnetism. Obviously, because we're working with AC electricity, we've got lots of magnets in play, electromagnets, and so we're going to talk a little bit about generating and those types of things as well. But I wanted to start out with these relays because this is a really good example of an electromagnet in use. And if you look carefully, you can see this relay right here and also this relay right here. They both contain an electromagnet. There's a coil inside this white wrapper and also inside this orange wrapper here. And what takes place, you can see real well with this relay, is what happens is we go ahead and we energize that coil, the 120 volt AC part, and there's a mechanical process that happens. You'll see down here in this corner, you see how these contacts, or this armature here, this metal armature, is attracted to the coil, and there's a mechanical process, and this switch down here either goes open and it closes. So it opens and closes at the same time, and that allows us the flexibility to do a couple of different things. So we might have a situation where the relay is not functioning properly, and there's some tests that we can perform as electricians to try to determine what's wrong with the relay and determine what's not functioning, either the mechanical part, remember that mechanical part that moves back and forth in there, or is it the electromagnetic part, the coil, that we're troubleshooting. So these relays are standardized. They are called 11-pin relays. They have 11 pins, and those pins correspond to 11 holes on these relay bases down here, and they're standardized so that we can either use, in this case I've got an Omron relay here, or I can use an Allen Bradley relay that I have here in my hand. So two different manufacturers. There's some subtle differences to the relays, but notice each one of them, if I insert it into the base here, that one will fit properly, and also this one will fit properly as well. So we're in a situation, our relay is not functioning properly. We need to do some testing of the relay. So I've got the meter over here, and I've got my dial turned to the audible signal. So I'm going to check for continuity on this coil, and anytime I'm using a relay, that coil should have continuity. So notice when I touch my probes together, I get that audible signal. So if I come down here on screw terminal number 2 and also screw terminal number 10, what happens? I get a short beep, which leads me to believe there might be some type of an issue with the coil on this relay. So it's not going to function properly. So my electromagnet isn't going to close or isn't going to energize. And in the case of the electromagnet not energizing properly, then my switching mechanism is not going to work properly. So if my electromagnet doesn't work, my mechanical portion does not go back and forth. So what do I do? Well, just so happens I have another relay here. Again, different manufacturer, however, fits into the 11-pin relay base. Slide that in, and now I can do my continuity check again, and notice what happens from 2 and 10. Now I have a good audible signal, so that tells me that the coil is good on that relay, and my process should be back functioning again. So very easy to determine if your electromagnetic portion is bad by doing a continuity check. So another advantage of using an electromechanical relay is, again, we've got this mechanical portion here, so we can do some switching. We can turn some things on, we can turn some things off. We can actually turn things on and turn things off at the same time, and I'm going to show you that function here in just a second. But the other concept is we can have different voltages present. So in this case, I might have 120 volts. That might be energizing the coil. However, I could be using a higher voltage or a lower voltage in the switching mechanism. So my 120 could be switching, say, a 240 volt circuit. So I could have a 240 volt light that I'm turning on. Or I could also run a lower voltage through those contacts. And in this case, I could be energizing this 24 volt AC coil on this relay. So sometimes relays are actually working hand in hand, side by side, doing different things. But the nice feature about a relay is I have typically a control voltage. That's the voltage that's energizing the coil, making that magnetic field and moving this mechanism. The mechanism then switches a higher voltage or lower voltage depending on the use of the relay. So electromechanical relays provide us with a couple of different functions. Typically we refer to them as normally open and normally closed. And if you look carefully at the relay, you'll see up at the top here we have some screw terminals, number 1, number 6, and number 11. Those are what we call commons. And those three commons have two other terminals that are in common with them. So in this case, number 8 and number 9 are in common with number 11. And if you follow this diagram here, you'll see that number 11 in relationship with number 8 is what's called a closed contact. So that means right now in the de-energized state of this relay, the coil is not energized. That tells us that that switch or that mechanical portion is closed. And so if we had say a red light connected to screw terminal number 8, we would have a red light on at this time telling us that our machine is in fact stopped or our process is stopped. Then we could connect a second light, a green light, over to number 9, and in the event that this relay becomes energized here on 2 and 10, so we just pushed a start button, we started a process. Now this contact is going to change state, and now our green light is going to be on and our machine is going to be running, and that green light is going to indicate that our machine is running. So let me demonstrate a little bit how that works. You'll see down here on this relay, I'm on screw terminal number 1 down here, and this is 3, so 1 is in common with 3, but notice there's no continuity here. There's no audible signal, and so that tells us that that's an open contact. If I move my red test lead over here to number 4, notice I get my audible signal, so that tells me that that contact is closed. And if I'm reach around here to the back side, I hope I can actuate this by hand. You'll see when I actuate it, notice how number 4 is open now. It changed state. So I can actually manipulate that by using my finger and opening and closing that mechanical switch. So we talked about number 4 being a closed contact. Here's number 3 again. It's open. However, when the relay energizes, it goes closed. So that's an example of how the electromagnet inside the coil moves and changes the mechanical state of those switches. One of the disadvantages of the electromechanical relays is they can only carry small amounts of current. You'll see the contacts inside there, not very large, not a lot of surface area. You start running a lot of current through a switch that small, and you're going to eventually burn the contacts up and probably even melt them inside of the ice cube relay. So what you're going to do is you're going to want to consult the side or the front of your relay, and you'll be able to determine the amount of current that this relay can carry through those switches, and that's typically always located right on the side of the relay.